In this class, we move to the some examples on the linear operation of op-amp. Okay, first of all, we do some revision. So in application of op-amp, it has two. It has two operation. The op-amp can operate in a linear operation region or operate in a non-linear operation region. Okay, so this week we cover the linear operation region. So the example of application that work on the linear operating region are the inverting amplifier, we have non-inverting amplifier, we have summing and subtractor. Okay, so how we can differentiate between the linear and non-linear circuit application if we are given op-amp circuit. So one of the way is by looking at the feedback. Okay, see the feedback. Okay, so for the linear operating region, the feedback is usually a negative feedback. The negative feedback. Okay, so if we have the symbol of op-amp here, this is inverting input, this is non-inverting input. So if we have the negative feedback is the connection from the output to the inverting input. So this is what we call a negative feedback. Okay, if the circuit has a negative feedback, so the op-amp is most likely to operate in linear operating region. Okay, so in a linear operating region, there are several things that we need to consider when you do the DC analysis. So the DC analysis. Okay, so for DC analysis, basically, first you identify the node. And then the second one, you write down the KCL. Okay, so the DC analysis of op-amp circuit always use, not always, most of the time use the Kcl equation. Okay, in the Kcl equation, you will have, you need to consider the current. There will be a branch that will be the terminal of the input. Okay, terminal of the op-amp input. For example, in the circuit, this is the current here. Let's say I put it I minus. So this I input here, the input current of op-amp is always 0 ampere in ideal model, because the op-amp has the infinite input impedance, so that the current is almost 0. So when you do the KCL, you can ignore this input current. After you do the KCL, so you have the equation made of the current. So the current can be expressed using the Ohm's law. Okay, so now you have the equation as a function of voltage, and then in the voltage you will have the V minus and V plus. Okay, in the op-amp, V minus is equal to V plus. This is what we call a virtual short. This is a virtual short. So the V minus will always force to be equal to the V plus. So you apply this one. So this is the, and then after that you solve the equation. Okay. Let's say if you are required to draw the waveform, draw the output waveform. Okay, so when you draw the output waveform, one thing that you need to consider is you need to consider the clipping effect. Okay, clipping effect is where the output voltage is much larger than the maximum DC supply, or the output voltage is more lower than the minimum. Okay, so that if in that cases it will limited by the DC source. So the DC source of the op-amp is our plus VCC and minus VCC. Okay, in the symbol, sometimes we put it here, this is plus VCC, and then this is our minimum limit, negative VCC. So the output, if the calculated output value is within the plus VCC and minus VCC, so there is no clipping effect. If the output value is exceed the plus VCC or much lower than minus VCC, there will be a clipping effect. Okay, so this is the summary of how we do the DC analysis of an op-amp circuit.